All right, good morning, everyone. This is David Green from Ancortek, and we are going to go ahead and start in about 2 minutes. Usually helps everybody getting in late or struggling with their computers. So we're going to go ahead and start at 10:32. So meet us back then. Okay, good morning, everybody. Thank you for joining us in. So today's topic is going to be on real-world applications with Ancortek's SDR, software-defined radars, and today we're going to be covering SAR imaging. My name is David Green. The organizer for this presentation is Elizabeth Weng, and yeah, so let's go ahead and get started. All right, so we have a lot of ground covered today. We're going to start out with an introduction to Ancortek, talk about who we are and what we do, and the products and services we provide. I'm also going to be talking about two products in particular, the software-defined radar kit 2482 and the 580AD. And so I'll give you a little bit more details about those kits and what we do with them. After that, I'm going to give you just a really quick overview on SAR imaging and so the kind of the operational work behind it, how we set up our SAR rail, and the processing that we do to make these images. I'm going to go over a few different imaging examples. We have some indoors, some outdoors, some with the 580AD, and then also the 2482. And then finally, I'll wrap up with a live indoor demonstration. We'll run the rail here in the lab and do that, and then we'll have a question and answer session for any questions or queries you guys have. Oh, and one more thing, if you can hold all your questions to the end so that we can get through this, you can actually start, if you have questions, you can start typing them out in the questions box, and when we get to the end there, I'll just go ahead and go through them one at a time. So it's really good to put them in order. All right, so Ancortek, who we are and what we do. So Ancortek, we're a small company based out of Fairfax, Virginia. There's a number of us, and we have a kind of a pretty deep knowledge on microdoppler analysis and radar signal processing, long history of technical research. And basically we saw this, we started out because we saw this market need for, not too many people were selling low-cost software-defined radars that had a high amount of capability or a high amount of flexibility. If you wanted to set up something like that in your lab or use it out in the field, you needed a whole bunch of different boxes. And so we took that as an opportunity. We saw the foresight in that, and developed our products. And we've gotten a lot of good comments and good feedback about it so far. Pretty well known now in industry. And our founder, Dr. Victor Chen, he's pretty renowned both in industry and academia, specifically with IEEE. He's a master at radar microdoppler signature analysis. He does time frequency-based radar image formation work and also inverse SAR. So what we do as a company is that we develop products, both hardware and software, specifically software-defined radar kits. So we sell these products, and we also develop different software applications to run them and GUIs and things of that nature. And then we do a lot of integrated solutions. So if you have a particular application, or if you want to look at, for example, studying microdoppler for UAV detection up in the air, or gesture sensing, or human occupational presence sensing, we do all that stuff. On the right, we just have a list of some of the applications we've done in the past, everything from traffic monitoring to, like I said, UAV detection, health-related projects, all different kinds of things that our radar kits are pretty good at. So the benefits of our product is that we've developed it's a coherent system. It provides both amplitude and phase to our processor, and you can send that out to the host and work with that. It's software defined, being that you can control the different output waveforms. We have a number of pre-programmed waveforms that you can use, and you can control the parameters of those. And they're reconfigurable on the fly. It's highly integrated. The device is very, very small, very lightweight, and low powered. You can fit it on a drone. You can fit it on just about anywhere, actually. We've put it in a number of odd places, both outdoors and indoors. And because of the range of frequencies that it operates at, it's very good for wall and ground penetration. Specifically, our 58 or 580 AD. Operating at 5.8 gigahertz. That's a pretty good one. And then you can also use it for a variety of things, such as non-contact sensing. So if you want to monitor heart or respiration rate of a patient without hooking up a probe or something, our products are very good at that. And they operate in all different kinds of weather conditions. Radar is very good at seeing through dust and rain and snow and different things. So it's a pretty good all-weather, day or night viewing platform. So why Ancortek? Well, we've done a lot of work in minimizing this technology, making it small, making it lightweight and compact, making it very easy for the end user to interface with the device, reprogram it, set it up. It works right out of the box, so when you order a kit from us, we include everything you need to get up and running. That includes the antennas, the power, the cable. The antennas are specific to the center frequency of the board that you choose, but when you order from us, you get everything you need to get up and running, and you can start, plugging away at MATLAB or plugging away at C++ or your other, whatever you're good at. And they're useful for all different kinds of applications. We've seen some pretty interesting work from customers and from our own in-house research team, and we sell around the world. So we have a pretty good presence. All right, so a little bit about the 580 AD. So this board operates at a center frequency of 5.8 gigahertz. The device comes standard at 400 megahertz of maximum bandwidth, but we can upgrade that. And then the AD stands for advanced. It's our second generation of products. So we've put in a fractional N PLL, a phase lock loop, and that really gives us pretty good linearity with frequency modulation, and that in turn enhances our target detection and improves our range resolution. The device comes with the AD module, so your actual RF front end, the FPGA processing board. It comes with all the GUIs that we developed in the libraries, as well as, like I said before, all the power cables, the antenna cables, the antennas, and then the enclosure. So everything you need to get up and running, this device comes with it. The 2482 is similar in that it comes with everything you need to get going. The differences are, along with the PLL, we've added a second receive line. So if you want to do I can't say that word this morning, interferometry, radar interferometry, or a bunch of angle of arrival, things like that, you can go ahead and do that with our product. And we've seen some cool stuff with that. It operates at a center frequency or at a range from 24 to 26 gigahertz with up to 2 gigahertz of bandwidth. So there's plenty of room to play around and see some cool stuff. So just if you're not familiar with software-defined radar or what most of our products do, we can output a variety of different waveforms. So everything from CW to FSK, but our most popular is FMCW. We've had a lot of customers work with that, and that seems to be the most in-demand thing. So if you take a look at, let me switch over to the pointer here, the spotlight. So this top part is the RF module on the front. So we start out with, back at the host side, down here, you connect to the device using USB. And so that's going to interface with our USB microcontroller, and you'll specify what waveform and what parameters you want to operate at. That's going to control a high precision DAC, which is going to provide a tuning voltage up here to the RF module. That tuning voltage will set the PLL and the VCO to whatever frequency you're running at. So for example, if you're doing FS or FMCW and you're doing a sawtooth, you'd start out at 0 or some low value, and you would ramp up. So that's what that V-tune looks like. And you can ignore the numbers here. This is all just representative. But essentially, you're making that voltage ramp. What that does is the output of the VCO then looks like this. You start out with a low frequency, and then it goes higher and higher and higher and higher until you get to that top voltage. And then when you repeat your waveform, it drops back down to 0 here, and this will drop back down to a low voltage. And so what it's going to do is it's going to split that waveform, that output waveform, and we're going to send part of it through a power amplifier, do some filtering, transmit it out into the real world. And then when we receive it, we do some amplification, some filtering again, and then we split it to our I and our Q chains, and those I and Q chains are going to mix it with a copy of our transmitted signal. And so what that does is it does correlation, and it de-chirp on receive. So what you end up with is this phase signal down here. When you have basically different targets will appear at different frequencies in range. And so you can do processing that way. So that data is then captured by our ADCs down below, goes into our FPGA. We do a little bit more filtering, and then we send it back out over USB to the host. So that's kind of how our radars operate. Oh, got to switch back to the mouse here for. There we go. Okay, great. So when we talk about SAR rail platform, SAR radar, synthetic aperture radar. Essentially, the notion behind this is that we have some, and I apologize for the crude drawing, but let me switch back over to the spotlight. We have some fixed rail right here, or some fixed path that our radar is going to be traveling on, and it's looking at a particular scene at a particular angle. So as it travels along, say this is the first shot, we go ahead and we take a snapshot of this scene right here. So we'll send out, maybe 64 sawtooth sweeps or something like that. Get those returns, we move a little bit, and then we take another snapshot. We move a little bit, we take another snapshot. And as we do this, what we're doing is we're increasing our distance, and that increases our aperture. We can do signal processing to essentially make it seem as if we have a larger aperture radar. And when we do that, that gives you higher resolution and the ability to see, all different kinds of features. So for example, if I just started off taking one snapshot of this car, from the center here, I'd get a really good indication of the range of the car itself. I'm going to see, maybe it'll be a little bit curved because different parts of the car will appear at different ranges. But as I move along this rail and I go ahead and I take snapshots of this car, I will start to see all different kinds of features of this car. I'll be able to see, how it folds, how it bends. Maybe the tires will reflect back differently at different locations. All different kinds of cool things show up, and it gives you a higher resolution image. So that's what we're going to be doing for the rest of this presentation. So moving on, this is our SAR rail platform. It's just something we put together in the lab. So we started out with a 2400 AD2. We also use this on the 580 AD. And we have a fixed rail platform. It's got a carriage, and we can control it with a servo motor. All through an embedded Linux platform. So we start out with our antennas. Well, no, actually here. We start out with the embedded Linux board. That's going to go ahead and it's running Ubuntu, and it's going to be running the control interface for both the radar and the rail. So we'll start out at some 0 or home position. We'll instruct the radar, hey, go ahead and collect, 64 sweeps, 1024 samples per sweep. I want you to use FMCW sawtooth with these parameters. It sends all that data to the radar. The radar is going to go ahead and process that. It's going to transmit out our sawtooth signal. It's going to receive those reflections, and then it's going to do its filtering and send that back to the host, and our host is going to go ahead and store that data. And then it'll go ahead and increment our distance. So it'll move that SAR rail just a little bit more. Take another snapshot until we've completed our run. Now, to make this work outdoors pretty well, what we've done is we've set up an RTK GPS system. So you don't see it in this picture; it'll show up later. But we have an antenna that we mount on the top here to give us pretty good GPS information and phase carrier measurements, and we correlate that with a base station we have out in the field, and then also, I don't know if any of you are familiar with CORS, but it's a nationwide service where you can get GPS correctional data to improve your own collections. So we have those two feedback systems help out our radar, so we can get a couple centimeters of resolution when we're out in the field, which is outstanding for a moving platform. All right, so let me go ahead and switch back over to the pen. All right, so when we get that data, this is more or less the processing chain that we do. For this presentation, you're going to see two different processing chains. One is a really basic FFT view of it. So we do FFT processing to extract range, and then we do FFT processing as we move down the SAR rail platform to extract our azimuth information. The second set of images that you'll see relate to delay and sum or back projection, and that's the operation that we take there. So we start out this processing chain by collecting our positional information. We run our sweeps, collect that data, and then incrementally we move down, however much we've set it to. And in most of our situations, we're moving down, an inch or half an inch at a time, but we can move down to just a couple millimeters if we want. What we do is that we extract the I and Q raw data from those collections. We do some I and Q balancing, reshape it into a matrix. We pull out the mean of that. We do some, filtering. Like I said before, we do FFT downrange, and that'll give us our range information. We apply autofocusing, and sorry, this is all a mouthful, or quite a long chain. After that, we go ahead and we run our back projection. So we'll compute our distance to our pixels in the imaging grid that we define, and that includes the round trip distance from the transmitter to the receiver. Convert those to indices. We null out any areas that we're not interested in. We're not interested in seeing anything a couple millimeters in front of the radar, or a couple, maybe a meter in front of the radar. We'll get rid of that, and then we perform our back projection, and then we go ahead and convert it to magnitude squared, do a Hilbert transform, convert it to log, and plot the images. So that's a lot. You can go back and this will all be recorded and posted online, so you can go back and take a look at that. And then we also have code and stuff. If you're interested, go ahead and email us. All right, so moving on to the examples. So we're going to start out with indoor SAR imaging using the 2482. So the way this was set up is that, let me switch back over to Spotlight. Okay, so on the left here we have just a diagram of the scene. So this is operating indoors in a lab, and then down below is the location of our SAR snapshots. So we started off on the right, that was snapshot 0. We move a little bit, take a snapshot, move a little bit, take a snapshot, all the way up until 47 or 48 snapshots. So that was 48. This is 47 inches, just under 4 feet. In front of us, we have a desk, very long desk, and we have a corner reflector that's fairly close. It's at about 3 meters. Behind that, we have some more desks. There's a metal filing cabinet here off to the right, and that's going to give us some really funny returns. And then we have this wall, and this is just a standard drywall. I think there's a whiteboard right on the other side, so that also gave us some funny returns. And then on the right, you can kind of see it set up. So we have the SAR rail platform. It's an older version of it. And this is our corner reflector right here on the left. And we have it aimed at the radar. So we should get a really, really strong return off of that. And you have to switch back to the pen every single time. All right, got it. Okay, so this is our antenna configuration for the 2482. And we change this around for different experiments. So we started out by having the transmitter down here on the bottom left, and then 0.055 meters, or yeah, is the receive channel, and we moved it up a little bit, and then down below we had the first receive channel. So we have 2 receive channels on the 2482. And we collect that data. We process them separately just to see what the individual channels look like, and then in some of the examples we'll process them together. All right, so this is them separate. So what you see, switching back to the spotlight quite a lot. So we start off all the way on the left here. This top plot is channel A, the bottom plot is channel B, and our zero range is all the way on the left. The y-axis indicates your azimuth. So as I move to the left, that's we're going up. As I move to the right, from 0, we're going down. So you can see channel B was actually pretty clear. Channel A, we had a lot of interference. But with channel B, you get a really bright return off of that corner reflector at the indicated range of about 3 meters. You get a bunch of other reflections, and this is actually that desk that it's sitting on. It starts from about 0.5 meters and extends all the way about to 3.5, 3.75 meters. There's a space, and then you get the that metal filing cabinet and the desks that are there, and then the wall. And so the wall gives you a pretty good return, and the corner reflector gives you a pretty good return. And this is imaged with 40 dB of magnitude. All right, so moving on. Okay, so what we did was we went ahead and these are the DAS, or delay and sum, or back projection results. And so the difference is that our FFT images are just going to give us, straight up FFT processing for range and straight up FFT processing for azimuth. Delay and sum, what it does is it goes by and through, and it tries to correlate in time the amplitude or the power of the signal that you received against the distance to each pixel. So for example, if I know that this pixel right here in the center where this target is, I can say, okay, well, if I want to add up all the energy that I got at all those different time instances from all of my different collections down below, and it sums all of that up. That's the sum part of delay and sum. So on the left, we have our channel A image, and you get this funny return from the desk, and then there's our corner reflector right there. And then on the right, this was channel B. You just see the corner reflector. This was with 40 dB of dynamic range, and these are the responses that we get. The advantage of delay and sum is you don't get a lot of the sidebands and stuff like that from the FFT processing and that we do before. So it's pretty good at that. All right, moving forward. And then this was a combined image. We did some time delay summations for both channel A and channel B, and that was the return that we got from our corner reflector. So it was pretty bright. So for the next example, we had a 1/2-inch stainless steel pole. These are really common in the electrical like power industry. So these are probably routed all throughout your office, and they carry 120 or 240 volt power inside around. And so it was about the same setup. We split the desks, mounted the pole in the middle there, ran our SAR rail just as before, and then we still have all of the other background stuff. So we have the desks, the filing cabinet, the wall. All of that is still there. And so this was the same setup. We had the transmitter at the bottom left, receiver in the middle, or the second channel receiver in the top middle, and the first channel receiver on the bottom right. And this was the response we get. So the pole was clearly it wasn't as strong, and so we saw a lot more information coming from the desks and coming from our environment. So the desks showed up really strong in this image, and then we also have the stuff in the background, and then the wall is really, really bright. But you can see the pole. The pole is there, and these are all really basic images. You can do some more work, either clean or other algorithms to clean this up. All right, so moving on. This was the delay and sum images. So essentially, it correlates the time and position and sums up all the energy. So we got a really nice return for the pole in both of those images, and we still got some stuff from the desk. All right, let's see. Okay, and then this was with A and B combined. So it got rid of most of the stuff from the desk from channel A, but we had some smearing. And so what was going on, yeah, I don't, okay. What was going on is that there wasn't actually a very good, channel A and channel B weren't lined up as well as I should have, and that relates to the SAR rail not being as exact as it should be. So we got a little bit of smearing between those two images, but that's something that could be worked out in software. All right, so the next one was we had the stainless steel pole in the middle of the desks in the same place it was before, and then we put that corner reflector out a little bit beyond it. So it shows up at about 3.7 meters. The pole is at about 2.5 meters. We moved it in, and then that corner reflector was also moved up a little bit. And then we rerouted, or we moved around our antenna positions. So we have the transmitter here. Receive channel 2 is down below this time, and then receive channel 1 is up above. And then this was the return we got. So this was actually a really cool return. So what happens is that we see the pole. The pole is there. It's weak. It shows up better in image B. Let me switch back over to Spotlight. It shows up better here in image B than it does in A. But we got this really funny smearing from the corner reflector, and then we get the background of the wall and some other things, and this was basically that basic FFT processing I was telling you about. This is unfortunately one of the artifacts of it. So objects that are not dead center are gonna smear like that unless you do additional processing, and I didn't do additional processing for this one. But it shows up really well in this image. This is the dual channel delay in sum image. So we have that corner reflector, and I actually flipped the X, the cross range for this image. But we have our pole in the center, and then we have that corner reflector, and it shows up really well at about the location that it should be. And so that fixed that up pretty nicely. So we then started playing around with different configurations for the antennas. So these horns are a little bit wider than they are tall. So we reoriented these into a vertical position. So we have our transmit channel up above, receive channel up above, receive one channel or first receive channel down below. But they're all vertical. And so that gave us some better results for the pipe. The pipe shows up a lot stronger. Our corner reflector is still there, nice and bright. And then we get the wall, and so this was the pole and the corner reflector here. All right, and let's see. So moving on. Okay, so this was another trial we did. Essentially, we wanted to start figuring out, what are the extents that we can do with the rail. So we ended up taking many more collections per sweep. So we got it down to 0.0048 meters per sweep. That's each of these here. And then we moved the corner reflector way off to the left of the desk. So it's kind of lined up with about the end of the SAR platform. And you could see it there on the left. This was channel A, this was channel B down below. So we had a nice strong return from that. And then these are blown up images. So we have the table is still showing up there in both of the images. We have our corner reflector sitting on top of the table. We have a nice space. We have our desks and that metal filing cabinet. That metal filing cabinet actually caused us a lot more trouble than I expected, but yeah, it was kind of funny. And then the wall. All right, and then in this one, we moved the corner reflector all the way over to the right, reran the same processing, and we see that the corner reflector is off here to the right, and we can blow that up. And so we have the desk and the back desks up against the wall. The wall's there. That's all the same, but we have our corner reflector has moved off onto the positive side of the azimuth. All right, let me switch back over to. Okay, so now we're going to go ahead and start with the outdoor SAR imaging for the 58080, and I'm going to take a quick pause. I did notice that I don't know if I'm lagging or if the audience's different audience members are having technical issues, but I'm seeing a bunch of I guess orange signal quality lights going on with different audience members. So I apologize if the webinar isn't getting through too well. This is being recorded and it'll be put on the website, so you can see it in its full quality there if you're having trouble viewing it now. All right, so let's go ahead and keep moving. So this was the setup for the 580 AD. This is a 5.8 gigahertz radar. We mounted the antennas on the front. I think we had the transmit on the top and the receive on the bottom. It's up off the ground. The image isn't to scale, but the scales are right. And then we had a little bit of separation between the two antennas, and then it's held up here on the radar rail. And we took this outside and did different collections, primarily in this there was a nearly vacant parking garage. So we set it up both underground and above ground. So in this one, we're aiming right at this is all concrete and asphalt, or concrete, I believe. I'm not a structural guy. I apologize. That's if I offended somebody and that's asphalt, but I'm pretty sure it's concrete. And so we have it facing out, and we did some collections, and so we get really strong returns from that. This part is actually a reflection, and then this part right here is that wall in front of us. So we see a nice strong return in the middle here from that little gap. And then we get these open spaces, and we lined up the radar so that it was looking right out in that situation. And then we went up top, and essentially we took a minivan, set up the radar so that it's looking at the minivan in different positions, and did our collections. So this was kind of the broadside of that passenger vehicle, and so you get this nice strong return from the vehicle at the range that it's at. And then if you look closely down here below, you'll actually see it start to curve just a little bit. And then the same thing with up at the top. And then I've kind of outlined where the vehicle was in that scene. So we move the vehicle back. So it's still broadside, but it's now down at 17 meters. And this was the response that we got. And you can see that more of that curvature now from the vehicle is showing up. And then we had this other little peak over here at 10 meters, and I don't know if you can see it too clearly in the image, but there's actually this pole right here that showed up pretty well, and then there's some other concrete features on the side, so that gave us those returns. All right, so now we went down below and we set up the car so that it was slightly slanted and took a picture of it with the radar, and this gave us a really cool response because you could see very clearly the curvature from the front of that vehicle. And then the back is still showing up. And you'll notice that there are these kind of vertical lines that are going up and down. They appear, and if you notice, it correlates to us being underground here. It's actually these slabs up in the ceiling. So the way that they made the ceiling of the concrete is that you've got these concrete slabs that are coming down, and they actually show up at periodic range bins on our images. All right, so now we're going to do some outdoor imaging with the 2482. And so before I get started with this, what I'm going to do is I'm actually going to start part of our live demo. So what I have here is I'll switch over to the webcam. So this is, and I apologize, the lab is cluttered, but this is the SAR rail platform that we have here. And let me see if I can switch over to full screen so that you can see what I'm going to do with this. Okay, here we go. So you should be able to see my screen. So what we're going to do is we can SSH into the device. And what I'm going to do is tell it to go ahead and start a collection. And so let's see. And so what's happening is that you can see it on the webcam now. You'll see it's taking pictures and it's going to start moving slowly. So it moves, takes a snapshot, moves, takes a snapshot, and then on the right here in our SSH session, you can see, okay, well we stepped this much. This is the current iteration that we're doing, and it's collecting all of these the sweeps and storing it as a binary file on the device. And when we're done, when we get back over to the live presentation, we'll go ahead and process those images and take a look at what we see. Okay, so let's get back to the presentation. And I'll leave that webcam up so you can see it. All right, so for our outdoor outdoor SAR imaging with 2482. Essentially, we took it to the top of another parking garage. And I don't know if any of you are familiar with the University of Florida, but they have a relatively new parking garage. I think it's about 4 or 5 years old, next to the, I believe it's the Institute on Aging. That's the white building here on the right. Let me switch back over to Spotlight. Can I do that? No, I can't. Okay, I can't have webcam and Spotlight. All right, but we're positioned where this orange triangle is on the top of the parking garage, and we're going to be looking down below at the street below us. And so these are the Google Map 3D images that we got. And then this was, we kind of like zoomed in, and you're looking down. We're about where that first white car on the left is, where the tip of this triangle is pointing, and this orange highlighted scene is the area that we're going to be looking at. So by some coincidence, the Google Map image has this white vehicle here. When we actually did this scene, there was a very similar white vehicle in the same spot, so I thought that was kind of interesting. But this is a photo I took from the radar up on the top of the parking garage looking down. And so this is what we should capture. And you can look off to the left, and there's not much there, and you can look off to the right, and there's that vehicle again. And then there's Gail and Miranda up at the top. So this was the how we had the radar set up. Let me see if I can. I'm going to turn off the webcam now so I can just use the Spotlight here. So this is how we had the Star Rail platform set up. We were at the top of this parking garage. And what we can do is we can adjust the angle that the radar is looking at. So we kind of tip that elevation or the elevation angle down, so it's looking down at the street. And I know some of you are seething mad right now. You're saying, "Oh, what are you doing with pointing that GPS antenna slanted?" And yes, you're right. It messed up our GPS signal a little bit. We still got pretty good results. On the right here, you can see this is the reference station that we set up. We still got pretty good results, but yeah, that's definitely not optimal for the GPS antenna. But we started on the right here, and we sweep to the left. We take those images and we process them. All right, so these were the first results we got, and they're a lot weaker than the indoor experiments, just because there was a much farther range this time, and the 2400 kind of caps out at about 30 meters, 30 to 34 meters, and so they're pretty weak, but they still show up, particularly in channel B. This was the we had a laser rangefinder, and we measured out the distance to that truck, and that was actually spot on the distance to it, and it appears a little bit to the right from boresight, and so it shows up at the right azimuth. And then up above here, I'm actually still not sure what that was, this spot right here, but it shows up in a number of other images. So I'm not sure if it's that. If we go back, there's this pothole. There was a fire hydrant, but those are a little bit too far out. It was something probably around here, but I'm not sure still. All right, and then this was the delay in some image, and that gave us a really good view of the truck and where its location was. Again, it's much weaker than the indoor experiments, but the truck was very, very bright right here. And we had some other stuff in front of the truck. Still, again, not sure what that was. It's a funny thing with radar imaging. You get all kinds of funny artifacts. All right, so we did 3 of these collections. The first 2 came out to about the same. Not much changed. Again, we get a really bright return from the truck on the right from channel B. We get that unknown response on the left, and it shows up at the range that the truck's at. And what we're going to do now is we're going to okay, there we go. This is the delay in some image for the second trial with channel B, and we get a really bright return from that truck right up here at the top, at the range and about the angle that it should be. And then we get some other kind of funny stuff going on. I'm not sure if maybe I walked by it or something. And then this was the third trial, and this was really funny because what happened was about halfway through the trial, we had a FedEx truck come and pull up kind of to the left, more in the middle of our radar, down below where that other truck was. So it presented this this little energy blob right here. So the truck still shows up nice and bright. But there's this FedEx truck that appeared for some of the collection, about half of the collection, and it's showing up right there. And we can actually see that also on the delay in some images right here. I kind of wish it had stayed around for the full, but they came in pretty quick, dropped off their package and headed out. But I was processing it, I was like, oh wow, that's actually pretty neat. So that's the energy return from it. All right, so let's switch back over to the live demonstration. So right now, let's see. Okay, so here's my screen. You guys should still be able to see my webcam. I'm not sure where that window went. See if I... Where is it? Okay, there it is. All right, so yes, that so what's going on now is that, oh, yeah, I got stuck. All right, there you go. There's a kind of a safety that if it goes too far, it'll eject the rod in the center. So the radar now is returning home. It finished its collections, and so it's coming back. But essentially what it did was it started out here, took a snapshot, moved about an inch, took another snapshot, moved an inch, took a snapshot, all the way until it got to the end here. It collects all that data on the embedded Linux platform, and we're going to go ahead now back to the screen. I'll go ahead and turn this off. And we will switch over to FileZilla, throw the SSH in there. And let me actually tell it to stop moving. I don't know if you guys can hear that or not. All right, scan complete. So we did, 96 collections. Okay, so it was moving every half inch. So this is the collection we have here. So what I'm going to do is I'm going to drop that into this folder. And that's going to go ahead and process. And what it's doing right now is that it's transferring all the, see if I go into this folder, it puts each of our collections, each of these collections is 64 sweeps, FMCW sawtooth sweeps that it received. And it puts each of those collections in a single binary file that MATLAB can understand. And so we're transferring that back over to our MATLAB directory, and we're going to work on that when it gets there. In the meantime, what I'm going to do is I'm going to get the name of this folder, and let me switch over to, okay, did that finish? Let's see. Those line up? Yeah, those line up. Okay, great. So what I'm going to do is I'm actually going to go into MATLAB, and we are going to run, where's our FFT approach? Put it there as well. So this was just the simple FFT implementation. Let me switch the screen just over to MATLAB now. Okay, great. This should update a lot faster now for you folks. Okay, so we're in MATLAB, and so we start off just by declaring our parameters and different radar variables that we're going to be using. We go ahead and process all of that binary data that we receive, form it into a matrix, apply more parameters. We determine, okay, what was the maximum range of this based on, you know, the information that I gave it, and then also how many collections it saw and things like that. And so it does all that processing. So when we're done, what we can do is we can go ahead and run this. And yes, we will change folder. And so it's now processing all of our collections, and this shows up really fast, just the regular FFT method. All right, let's see. I'm actually trying to make sure that you guys can see this because I'm not getting any indicator from. Yeah. Okay, great. You can see this. Okay, great. So these are the range azimuth images that we generated from our sweeps. Channel B came up pretty well, and so what I'll do now is I will. Let me go back over to the webcam just so that you guys can get a good understanding of the room. So we have the radar here, and from where I'm sitting, I'll move it back here. So I'm sitting here at this table. So from the table over to the radar, it's, I believe, 3-ish meters to where I'm sitting. And then off to the side, what the radar is looking at is we have the wall at about 5 or 6 meters, and then we have just a metal desk here, a microwave. But this whiteboard, the whiteboard here is also pretty reflective. So you get all of that in the image. So we go and turn this off. So if you look at, for example, channel B, and I will switch back over to Spotlight, what you see is that here's the wall at about just before 5, or maybe this is the wall here. I need to measure this out. But essentially, I should be a little bit off to the right. And yeah, that's probably me right there. I should have set up the corner reflector for this. That would have been good. So we get those returns, and then what we can do is we switch back over to pen. We'll run that delay and sum implementation. I hope this came out okay. There we go. That's the nice clean image from delay and sum. And let me see if I can blow this up for you guys. Okay, great. So those are that's the return there. So we get that's probably the wall showing up at about 6 or 7. I'm not sure what's going on the sides here. That may be me. I need to measure this out. And then there's some other stuff going on. Different parts. This could be the tripod, actually. That's set up here holding the camera. All right, great. So that concludes the live demonstration. And so let's head back over to the PowerPoint. So now what we're going to do, let me switch back over to the PowerPoint. Okay, great. So let's go ahead and start our question and answer session. So what I'm going to do is I'm going to start reading off all of the questions and stuff that we have. So if you have questions, please start dropping them in that question box. In the meantime, if you have further questions or if I can't get to your questions, you can always email us at info@ancortek.com, call us up, or if you're in the Washington, D.C. or Fairfax, Virginia area, we'd love to have you over and give you an open tour. So we'll go ahead and start out with this. So the first one is from Kim Lee. On the sawtooth input graph, shouldn't the y-axis be voltage and not frequency? This is the input to the VCO, correct? And that is probably a mistake of mine. So yeah, let's go back and we'll check that out. So that was way up here. Yes, you're absolutely correct. So the input going to the VCO and the PLL, that should be voltage, yes. Yeah, thank you for catching that. I appreciate that. So let me see if I can, I'll go through and type these out later. All right, are your radars designed to stay within the FCC limits for the 5.8 gigahertz ISM band, antenna gain, and RF power output limits? That's from James Taylor. The answer to that is yes, and if you want more information, go ahead and email us and ask us those specifics, and we'll send you over all of the, you can actually find a lot of that on our website. We have a lot of the power outputs and things like that on the website. We have documentation for each of our units, but yes, we fall within the FCC, the US FCC limitations for that. All right, next question. I believe that your method that the kit contains I believe that you mentioned that the kit contains multiple horns. Does the software support bistatic collections? Right now, the GUI that we have, no. The software, it'll collect from, in the Windows GUI, we can collect from one or the other. But in the C++ examples, we can collect both at the same time. Or in MATLAB, you can collect both at the same time, and then you can do the processing. But we don't have that implemented at the moment. Again, that's just a software thing, though. It's pretty easy to set up. So the next question, during indoor imaging, did you have any problems with reflections from the wall behind the antennas from either antenna back lobes or multiple times around returns? If so, how are they suppressed? The answer to that is yes. Yes, we had lots and lots and lots of reflections, and in particular, let me go back to that. Let me go back to that scene. There's this one metal filing cabinet that just gave us all kinds of ghosts and funny images. Yeah, this one here. Switch back over to. Yeah, so this scene in particular gave us all kinds of funny stuff, and so what happens is that we have this lab, and then right on the other side of the lab, at the wall on the top here, is another lab, and we have people moving around and all kinds of stuff in there, and that's actually where we got the idea to do some of the through-wall sensing webinars, because we could see those people very clearly. So we got reflections from or returns from people on the other side of this wall. We got returns from we have metal desks that kind of like line the perimeter of this office. So we got returns all over the place. So most of the images that you see, yeah, they were pretty controlled for the collections that we did, and then how we process the images for indoors. Outdoors, we just showed everything, but indoors you got all kinds of returns, and it was actually pretty funny. All right, next question. For the 24 gigahertz outdoor trail, with the truck at around 25 meters, what was the output power EIRP being transmitted by the transmitter? That's from Mr. Kimley. I don't know offhand, but you can check it out. The output power is, it's on the specification sheet. I forget at the moment, but if you either send us an email or check out the website, we have the IRP listed there. All right. Do you also balance the INQ channels in software? Yes, we do all of our INQ channel balancing in software. That was from Israel. Next question for SAR. I understand that you need to move the radar linearly capturing every increment at about an inch. With ISAR, where the target is moving and the radar is fixed, we cannot guarantee the target moving linearly. Is this processing done differently for ISAR? Yes, that processing is actually a bit different. I don't have any ISAR examples that I can give you, but yeah, that processing is different. I can elaborate further in either an email, or if you want to give us a call, we can talk about that. So the next question: what Linux computers are you using to control the radar with? So most of the distributions I've used are Ubuntu 14 and 16, and then also Arch Linux. That's for the C++ library, and that works really well. But it also runs great in Windows. Personally, I haven't tried it on a Mac, but that's only because I don't have a Mac. I need to wrangle one up one day and try it to see if it works. But yeah, it should work fine with Windows 7 and above, and I've tested it out on Ubuntu 14, 16, and Arch. And those were both from 64-bit distributions, as well as our embedded Linux platform is a Raspberry Pi 3, so it's the I forget the name of that distribution, but yeah, so it works great on that. Really, the controller for the radar is all done through libUSB. It's an open source interface that you can Google it, libUSB, and they have a number of distributions for Windows and Linux, and it's very easy to control the radar and set up the parameters and play around with it. All right, so can it be used as a receiver only? And that's from George Atkinson. And so the answer for that is no. And the reason being is that if we go all the way back up to the top, and it is on, here we go. So slide 9, I kind of show you, we can't use it as a receiver only, because what's going on is that those mixers are going to mix the transmit signal with the receive signal, and this is all done in hardware. This isn't done in software, so we don't actually offer control over that. So right now we actually have to transmit something. Now you can send out just a constant tone, but no, we can't do receive only collections, and that's just because how we have the hardware set up. All right, the next question from Junlin, why we don't have those connectors between the antenna and the device? I'm not, if you could elaborate on that or shoot me an email, I can try to figure out what you're talking about, but we have, why we don't have connectors between the antenna and the device? Yeah, if you could elaborate that, either give me a call or send me an email, I can try to better understand your question and give you a response for that. Next question from Rob Frizzle. What's the price for the kits? go ahead and if you can also email us on that, we can set up a quote for you. But that depends on which units you're getting and stuff. So we'll be happy to send you a quote or give you more information. All right, does it have a 10 megahertz reference input? That's from George Atkinson. Right now, no. This is something that we've kind of been looking into because we want to do like MIMO or multiple units kind of sync together. But right now, no, it doesn't. They all operate on their own. They all have an independent crystal that they use. So no, we don't have any kind of reference input for timing. All right, so first of all, thanks for this presentation. My question is, well, thank you. Yeah, what is about the SAR of rotating very good conducting cylinder? Is there a difference between rotating one and stationary one? So I think you're asking, do we get a different return or a different response from a rotating cylinder rather than a stationary cylinder? And I'm actually not sure. I can test something out in the lab. I believe you do because I think they do a lot of work on missiles rotating and stuff, and that seems to be different than stationary cylinders. But if you can send us an email, or I can try something out in the lab, and I can get you those returns or those results. All right, next question. How do you attain the azimuth in the radar? That's a great question. So the azimuth information is collected in two different ways. So I do two different methods for processing. Let me see if I can get back to a good slide for that. Okay, so this is a decent slide for that. Not the best, but this will work. So essentially, when I get the data, what I can do is that I have you have to remember, as the radar moves, it's going to be sending out 64 different FMCW sawtooth sweeps at each location. I can take one of those sweeps, and if I just FFT that down range and do a little bit of filtering, I can extract range information. That'll give me range information of all the objects around me from that one sweep of everything that the antenna was looking at, or from that one collection point. As I move the radar down and I take multiple collections, I can extract the range information from each of those sweeps, and then I can look at the differences in time, or I can do an FFT kind of across across the motion of the radar, and that'll give me the azimuth information, and I can pull that out. That's just using the basic FFT implementation, and this is all just like textbook stuff. Or you can do delay and sum, and delay and sum extracts both the range and the cross range information by essentially lining up the time delay from a pixel with the sample that we received it at, and it looks at all of your collection points, and it sums all that energy up together. So those are the two different ways that we do that. If you want more information on that, again, just email us, and we'd be happy to explain it to you. All right, next question. Can you explain why the GPS is absolutely necessary when you're moving in very well-defined steps on the motor? And that's from Joseph Spencer. That's actually a really great question. So for most of the collections, we don't use the GPS. The stepper motor I have in there and the controller for it is spot on. It moves very precisely. I think it's 16 steps. What is it? It's I'm kind of embarrassed, I forget now. But essentially, I can move it in revolutions, or I can move it in steps, and it's down to millimeters per step, and it's very accurate. So I haven't actually had any trouble with using just the servo motor with getting distance information. The only reason that I started using the GPS at the end was that I was doing so many collections outdoors, and you'll do a collection and then you move a little bit and you do a collection, and when I got to taking notes and actually correlating that all together, and it's like, oh, well, that one looks like it's a little bit more to the left than the right, it became a problem. So I threw the GPS on there, and of course GPS on its own only gives you, I think worst case it's 2 or 3 meters. So we used this open source software, RTKlib, and a separate base station, and then the Chorus base station over at the airport to give us really spot-on GPS results. So essentially, I knew where the collections were when I took them, not necessarily where each position or each step in the radar was. But yeah, so you don't need it as long as you have a pretty well-defined knowledge about where the radar is and what you're looking at. All right, the next few questions are from George Atkinson, and that's what is the transmit power, and then also what is the TX-RX isolation. The transmit power, I apologize, I don't know that offhand, but it's in our spec sheet online, and we have that listed for each of the devices. If you go to our website, you can go under products up at the top, and we give you all that information. For the TX-RX isolation, we have measured it. I don't know if it's in the spec sheet, but if you shoot us an email, we can go ahead and give you that information. All right, getting to the last few questions here. So is it capable to work with higher frequencies, and what is the limit? So right now, the 2482 is the highest module we have, and it goes up to, it sweeps from, what did I say before? I think from 24 to 26 gigahertz, something like that. However, so those are the hardware capabilities. However, a lot of that is limited in software because we have to stay within FCC regulations. But as I mentioned before, we sell worldwide. So in other countries, those limitations aren't there, and so you can use those additional hardware capabilities on the radar. And the highest frequency is 27 or 26 gigahertz. Don't quote me on that though. Check the spec sheet. It's in the spec sheet. But essentially, it's I think it's up to 2 or 3 gigahertz of bandwidth that we have. All right, so the next question is from David Long. Can multiple units be coupled so that only one transmits, but you do receive from the slave units? Right now, no. That's so you're essentially asking if we can build a MIMO system, and right now, no. We're looking into it, and it's a really cool idea, but it takes a lot of very careful steps to implement properly, and so that's something that we'd like to do, but right now, no. All right, next question. We have bought the SDR kit 980B. Oh, great, thanks. Hence, the processing module is the SDR PM402. Can we buy another front end? And that question is from Israel. Yes, yeah. So the you can look at, I'm trying to think of where you'd find that on the website, but essentially under all of our products we list what boards they're capable with, but the RF front ends are interchangeable. But they're specific to, if you have like the 580AD, it needs to work with the SDR PM402 or something like that. So take a look at that. If you have any, like we can, that's better for email, so we'll send you an email and get to that. All right, the next question is someone's email address, so I'll skip over that. All right, what is the size and the weight of the device? That's from George Atkinson. I am not actually sure what the weight is, but I can give you a rough estimate of what the size is. So I'm gonna go ahead and turn the webcam on, and what I'll do is let me walk on over to. I'm gonna grab another unit. Hold on one second. All right, I apologize for that delay. So essentially, what I am showing you now is this is kind of the enclosure, and the enclosures are the same in size for our different units. So this is the 580 AD, and just to give you a comparison, this is my phone. So it's a what is this? This is a Samsung S5, I think. So it's about the size of my phone. It's a little bit bigger, but about those dimensions. And this is just it's a smartphone. It's not a I think they're called phablets. I don't know. I don't keep up with that, but so those are about the dimensions of what the units are, and they all have the same size of the enclosure, and then the processing module and then the RF front end are about the same size. So that gives you some kind of idea. We can send you more pictures if you want. Just go ahead and send us an email. All right, last two questions here. Why don't you obtain the cross range directly, because back projection algorithm can do that? Yes, it does actually. I think we do obtain the cross range directly. Let me, if I'm understanding you right, you're asking me since I'm doing back range or back projection already, that already gives me my cross range information. And yes, it does. I think in the back projection or the delay in some images, I show the cross range down at the bottom, and then the range up at the top. But I may be misunderstanding your question. If you can give me a call or email me, I'll try to answer that. And then the last one from Kimberly, thank you, very informative. Oh, thank you, I appreciate that. Yeah, I look forward to your emails. And again, any questions or additional things that you guys would like to know or like to see, you know, we're an open book. We'd love to show you what we got, and we actually like showing off. So it's a pretty cool product. All right, so let me switch over to back to the presentation here. All right, so this was, so again, if you have any questions, it's info, I-N-F-O, at ancortek.com. This is our website here, www.ancortek.com, our phone number, our mailing address. All of this is recorded online if you want to see a repeat of it. We also have quite a number of application examples and demonstrations and videos online as well, if you'd like to see other things that we do with this radar and other things that our customers have done with it. You can find all the data sheets online. We have some research material. So yeah, feel free to get a hold of us or contact us, and we'll help you out. I want to thank you all for joining us. I'm going to have to go ahead and put it to a close. Sorry we went about 6 minutes over, but yeah, thank you all for joining us, and have a great day. Thanks.